Hi everybody. So in this video I'm going to show you how we can use logs to set up models that explore trends of data. And this is all to do with the equation of a straight line graph and the rules of logs. So we'll work through this example and I'll show you what I mean. Okay, so in example 1, we're told that the graph represents the growth of population of fungi over t hours. We've got a gradient of 0.8 and an intercept of 1.5. And like biologists suggest that this growth can be modeled with this exponential model p equals ab to the t, where a and b are both constants. For part A, we've been asked to write down the equation of a line in terms of p and t. So this bit's fairly simple because we know we've got a straight line graph, and this follows the standard equation y equals mx plus c, where m is the gradient and c is the intercept. Now we just have to organize this into the context of the question. We can see that y is the log of p. We've been told that the gradient is 0.8. Our exploratory variable x, we're told is t when this is measured in hours. So we'll say 0.8t. And then we're told that our intercept is 1.5. This is the equation of a line in terms of p and t. Then for part B, using your answer to part A, find the values of the constants a and b. So this is where we apply the rules of logs. We're being told that this has an exponential model of p, and you can see here that we've got the log of p, so we need to take the log of both sides of this model. So what we need to do is to use the rules of logs to make this right-hand side look something like the equation of a straight line graph, and then we can match the terms between the gradient and the intercept. So the first thing we can do is we can split this up using the multiplication rule. So we've got the log of a plus the log of b to the t. And I should say as well that we're using log to the base 10. Now we can move this t down in front of a log using the power rule. And then to make this look like the equation of a line, I'm going to put this term first. Then you can see that the log b term will be our gradient, 0.8. And then the log a term will be the intercept of 1.5. So if we say that the log of b is equal to the gradient 0.8, we can work out b by taking 10 to the power of both sides, because that's the opposite of log. So b will be 10 to the power of 0.8. And we can work this out and we get 6.31. And then we can say the log of a is equal to the 1.5. We'll take 10 to the power of both sides. So a will equal 10 to the power of 1.5. And this will give us that a is approximately 31.6. So now, for our exponential model, we can substitute a and b into here. So we get p is equal to 31.6 times 6.31 to the power of t. And then for part C, interpret the meaning of a constant a in this model. This is referring to the 31.6. When t equals 0, then this term will become 1. So we'll say that 31.6 is the initial population when t equals 0. Okay? Let's try another question. Okay, so in this example, we're told that a researcher conducts an experiment and records the following data for two variables x and y. We have this in the table. The researcher is told that the relationship between x and y can be modeled by this equation. We've been asked to plot the values of log y against x, and then use an appropriate straight line to find the values of a and b. So if we're going to plot log y against x, we need to take the log of each of these y values. So the log to the base 10 of 5 will be 0.7. Of 15, it'd be 1.2. Of 45, it'd be 1.7. Of 135, it'd be 2.1. And then 2.6 and 3.1. Now we need to plot the x values against the log y values. And then from this we can draw in our line of regression. Now we need to use this straight line to help us find the values of a and b in our exponential model. And you can see we've got to take the log of y. So if y equals ab to the x, then the log of y will be the log of ab to the x. And then we can split this up using the multiplication rule. And we can bring this x down using the power rule of logs. So now you can see that the log of b is multiplied by x. And this will be the gradient of our straight line. And the log of a will be the intercept. So we need to find the gradient and the intercept from this line. To work out the gradient, I could choose any 2 points. I've chosen this point and this point. We know the change in x is from 6 to 1, which is 5. And the change in y will be the difference between 3.1 and 0.7, which is 2.4. So the gradient will be 2.4 divided by 5, and this will give us 0.48. And we know this is the log of b. But then to find the log of a, we need to find the intercept, and I think this is approximately 0.2, and we know this is the log of a. So now we can solve this equation to find b, and this equation to find a. So now if we take 10 to the power of both sides, we'll get b is 10 to the power of 0.48, which is approximately 3.02. And the log of a is 0.2, so a will be 10 to the power of 0.2, which is approximately 1.58. And then we can substitute each of these constants into our model. So y is equal to 1.58 times 3.02 to the power of 2. Okay. Well, thank you very much for watching. I hope that's given you an idea on how we can explore nonlinear trends using exponentials. If you did find it helpful, please like and subscribe. And you can download the full lesson from my website, mrmathematics.com. I'll leave a link in the description below.